Hello and welcome, Mr. Johnson here, and in this video we're going to be looking at balancing equations. Now in textbooks this can also be referred to as balancing chemical reaction equations or balancing reaction equations, but most chemists just refer to it as balancing equations. And in this video, as we go to balance equations, we're going to look at two methods. The first of those is what's called the trial and error method. And this is the method that you're most likely going to find in your textbooks. Okay. The second method is what is called the algebraic method. And don't get scared by the name. It's not as bad as what you might think. But the algebraic method is a method that you're most likely not ever going to find in a textbook. It's a unique method that was actually developed by my high school chemistry teacher. And it's something that I've passed down to my students. I've even shown this to college professors. And they seem to like it. Not that they teach their students the method because, again, it's not in the textbook. But it is a fast, easy method to balance equations as long as you've got some math skills under your belt. Okay, but we're going to start out with trial and error and then look at the algebraic. Now, as always, before we start looking at the actual process, we need to get some terminology out of the way. So first off, what exactly is a chemical reaction? Well, this is just where we take one or more substances and we change those into one or more different substances. They undergo a chemical change. And hopefully, back in physical science, you learn the difference between chemical change and physical change. Well, anytime that there is a chemical change, that means that we've carried out a chemical reaction. And a chemical reaction is composed of two parts. The first of those are your reactants. These are your original substances. This is what exists before they undergo a chemical change. Within a reaction equation, these are going to be found on the left-hand side of that reaction equation. Okay? Within the reaction equation, there's an arrow that we read as yields or goes to or produces, and reactants are always going to be found on the left side of that arrow, unless you're talking about a reversible reaction, but we're not going to be talking about reversible reactions in this video. Okay? The second component to a chemical reaction are your products. And your products, these are the newly formed compounds, the newly formed substances. It's what's produced after that chemical process has occurred. And for products, we're going to find these on the right-hand side of that chemical reaction equation arrow. Okay? So we've got the basics of a chemical reaction. Reactants form products. But there's a key point in this that when we write out a reaction equation, we may not end up with the same number of each type of element as what we began with. We might end up with fewer carbons or more oxygens. And it makes it look like we've somehow converted one type of element into a different type. And that can't happen. Okay? We have to abide by this thing called the law of conservation of matter or law of conservation of mass. Again, hopefully you learned this in physical science. But pretty much what it says is that mass or matter can neither be created nor destroyed. It's simply transferred or it's transformed. Okay? This goes all the way back to this guy, Antoine Lavoisier, from France, that developed this idea of law of conservation of mass. Okay? We've since seen the addition of law of conservation of energy, and then you got Einstein that comes in and combines the two, law of conservation of mass and energy. This, for balancing equations, we're just looking at law of conservation of mass or matter. Okay? And what it means in terms of a chemical reaction in balancing equations is that the number of atoms for each element in that equation must be equal on both sides. For example, if I start with 5 carbons, then I have to end with 5 carbons. If I start with 8 hydrogens, I have to end with 8 hydrogens. That's how we conserve mass. Okay? And in doing so, what we find is that this may end up requiring us to change the coefficients or the numbers in front of the chemical compound. We do not ever change the subscripts on a compound, because if you change the subscript, you change the composition of that compound. So how do we go about balancing? Well, trial and error first, and these are your steps. The first thing we want to do is identify the reactants and the products. Okay? Now for this video, we're actually going to start at step 3. But step 1, you're going to see an example of this at the very end of this video. And this is where you have a written out statement. For example, hydrochloric acid reacts with sodium hydroxide to produce water and sodium chloride. You would have to take that sentence structure and determine what are your reactants, what are your products. And once you've done that, then it's step 2, where you're going to write out that chemical reaction using appropriate chemical formulas and appropriate symbols. Then step 3, where we now count the atoms and balance out those elements and those atoms, again, by changing coefficients, not changing the subscripts. And a nice little helpful hint for you. Always start with elements other than hydrogen and oxygen. In fact, leave those for last because quite possibly they're going to show up in multiple reactants and products. And if that's the case, and you balance oxygen in the first substance, and then you go and balance a different element, it may throw your number of oxygens off, and then you have to repeat the process. So we typically save hydrogen and oxygen for last, if at all possible. Once you think you've got it balanced, step 4, probably the most important step, double check. Because again, if you've balanced one element, and then you go and balance another element that's in that same compound, you may throw off your number of that first atom that you balanced, and now it's no longer balanced. So we always want to double check by recounting the elements in our final reaction equation. So let's go on and take a look at some examples. So the first example that we have is this one of hydrogen peroxide decomposes into or yields water and oxygen. So in balancing this, when we start out, all of these blanks, and I use the blanks just for an indication that that is the only thing I can change. And when I look at the blanks, it's understood that each blank has a 1 in it. We just don't write 1s. And what we're doing is the coefficient times the subscript. For some reason, my pen is not wanting to write, so bear with me. So try to get that figured out. There we are. So coefficient times the subscript. So starting out, I have 2 hydrogens, and on the product side, 1 times 2 would be 2 hydrogens. As far as my oxygens, 1 times 2 would give me 2 oxygens. And on my product side, 1 times 1 would give me 1 oxygen, plus, because I've got oxygen in more than one substance, 1 times 2 would give me 2 oxygens for a total of 3. So currently this reaction is not balanced. So I have to change up these subscripts. They can't remain as all 1s. So in changing subscripts, I'm going to balance out my oxygens. So in doing so, because I've got 2 in that O2, and I only have 1 within the water, I can think mathematically that if I put that coefficient from a 1 to a 2 in front of water, now I'd have 2 times 1 for 2 oxygens, still plus another 1 times 2 for 2, and that would give me 4 total oxygens. And I can see on my reactant side that if I change that coefficient from a 1 to a 2, then 2 times 2 would give me 4 oxygens. And I'd be balanced for oxygens, but additionally, 2 times 2 would give me 4 hydrogens, my reactant side, and on my product side, 2 times 2 also equals 4. So I'd start out with 4 hydrogens and 4 oxygens, and I would end with 4 hydrogens and 4 oxygens. And this would be balanced. The only other thing that I would need to do is go back and erase that value of 1 in front of O2, because again, we don't write a 1. So this would be balanced as 2, 2, unwritten 1. Now, some textbooks, what they will tell you to do to kind of visually see this is to draw out just a basic Lewis dot structure. So I would have my hydrogen peroxide, and I would have my water and my oxygen, and I can very easily see in my 2 hydrogens that I started with, my 2 hydrogens that I ended with, my 2 oxygens that I begin with, but my 3 oxygens that I end with. So by adding in a second water, I now have my 4 oxygens, and by adding in a second hydrogen peroxide, I would have my 4 oxygens, but also my 4 hydrogens and my 4 hydrogens. And they will ask you to draw this out in picture form. And if that helps you, then do so. So that is the first example. Second example, iron plus oxygen yields Fe2O3, or iron 3 oxide. So this is a little bit better example of trial and error. And the whole purpose of the trial and error is that you try something, and if it works, great. If not, then you try something else. So when I start out, I notice that I have just 1 iron, but I finish with 2. So I'm going to change this coefficient in front of iron to a 2. So now it gives me 2 irons beginning, 2 irons ending. And then I can look at oxygen. I start with 2, I end with 3. Well, there's nothing times 2 that will equal 3 other than a fraction. And we don't want fractions. So instead, for trial and error, I look at lowest common multiple. And between 2 and 3, lowest common is 6. So 3 times 2 will give me my 6 oxygens. And then as a product, 2 times 3 will give me my 6 oxygens. But now, 2 times 2 is 4 irons. So this value of 2 that we tried initially, and it worked for a period of time, turns out to be in error. So I have to go back and change it. So now I've got 4 times 1 for 4 irons on my reactant side, 2 times 2 for 4 irons on my product side, 3 times 2 for 6 oxygens on my reactant side, and 2 times 3 for 6 oxygens on my product side. And we'd be balanced as 4, 3, 2. Let's take a look at another example. So this one a little more complex. Now I'm dealing with a polyatomic ion, that PO4, that phosphate group within parentheses. But I'm going to show you something that we can do to kind of shortcut it. But I'm going to start out with magnesium first. I note that I start with just 1 magnesium, but I end with 3. So I want to change the coefficient in front of magnesium to a 3. Then I look at my hydrogens. I start with 3, end with 2. So lowest common multiple would be 6. So I want a 2 in front of the H3PO4, that phosphoric acid. And I want a 3 in front of my hydrogen. So that way I end up with 6 hydrogens beginning, 6 hydrogens ending. And now for the PO4. I could very easily balance each element. For example, 2 times 1 is 2 phosphorus. And then over on my product side, that unwritten 1, times 2 would be 2. And then I factor through 2 times 1 would be 2 phosphorus. I could do the same thing with oxygen. 2 times 4 is 8 oxygens. 1 times 2 is 2. And then factor through 2 times 4 would be 8 oxygens. So it turns out that my phosphorus and my oxygen are already balanced. But because PO4 occurs the same on both sides, instead of balancing it as phosphorus and then oxygen, I could also think about the fact that this is really PO4 with an unwritten set of parentheses and an unwritten 1. So 2 times 1 would give me 1 phosphate group. 2 times 1 would be 2 phosphate groups. And on the product side, 1 times 2 would give me 2 phosphate groups. And I can balance it as a group. So either by individual elements or by the grouping. But either way, I get a balanced equation as 3, 2, unwritten 1, 3. So the last equation for trial and error. Right? Again, a little more complex. So let's do this. And again, at any time, if you want to pause the video, attempt these for yourself, and then unpause and see me working them to verify that you're doing it correctly, please do so. So when I look at this and I see my nitrogen, so again, I'm going to think about that. 1 times 2 is 2, and then factor that through. 2 times 1 would give me 2 nitrogens. And on my product side, I have 1 times 1 for just 1 nitrogen. So I need to change that coefficient to a 2. So now I've got 2 nitrogens. Next thing I'm going to do is save my hydrogens for a little bit later, because I noticed that I've got hydrogen in my first reactant and hydrogen in my second reactant. And then on my product side, I have hydrogen in one of my products and hydrogen in the second one. So I'm going to wait on balancing that hydrogen, just like the little helpful hint that I gave you at the beginning. And I'm going to go on and look at my carbon. So I have 1 carbon starting, 1 carbon ending. So carbon's already balanced. That's good. My oxygens, again, I have it in 2 reactants and I have it in 2 different products. I'm going to save it to the end. So I'm going to go on and look at my sodium. So I start out with 1 times 1 is 1 sodium. I end with 1 times 2 for 2 sodiums. So I need a 2 in front of that sodium hydroxide. And again, take note, if I had gone on and balanced my oxygens and then balanced sodiums, I very well could have had to have changed my coefficient in front of the NaOH, which would have thrown my oxygens off, and then I would have had to have rebalanced them. So that's why we waited till the end. So now that I've balanced out my nitrogen, I've balanced out my sodium, I've balanced out my carbon, I'm going to go back and now look at my hydrogens. So 1 times 2 is 2, and then 2 times 4 would be 8 hydrogens. And I already have 2 times 3 for 6. And then that 2, I forgot my little blank out in front of water, my apologies. So 1 times 2 would be my 8 hydrogens. So it turns out that, forgot, 2 times 4 is 8 hydrogens, plus, forgot that I've got it in 2 different compounds. 2 times unwritten 1 is another 2, for a total of 10 hydrogens. Over here, 2 times 3 is 6, plus initially that 1 times 2 would just be 2 to give me just 8. So what I want to do, I don't want to change my coefficient in front of NH3 because it'll throw off my nitrogens, and then I have to change coefficient over here, which would change my carbons, and I need to change this coefficient. So instead, I want to change the coefficient in front of water. So I'm going to try a 2 and see what happens. Now I've got 2 times 2, which would give me an additional 4 hydrogens. And now my hydrogens are balanced 10 and 10. Finally, my oxygens. So for oxygen, I have 3 plus 2 times 1 is 2. So I have 5 oxygens. And on my product side, 1 times 3 would give me 3 oxygens. Plus 2 times 1 is another 2 for 5 oxygens. So this is balanced out as 1, 2, 1, 2, 2. Now that's kind of hard to see that 2 in front of the water. Again, my apologies that I forgot to put that blank in there. And this would be a balanced equation. So that is how we balance out by trial and error. Next thing I want to show you is how to balance out algebraically. And again, algebraically, it's not as hard as what it sounds. There are more steps to it, and you do have to be a little more careful. But if you run into issues on balancing an equation, algebraic method can help you. Okay? As long, again, as you've got some math skills under your belt. So let's look at the steps, and then we'll look at a couple of examples for this. All right. So algebraic method. The first thing we do is we label each substance within the reaction equation with a letter, A, B, C, D, etc. Then we're going to list each element present in that reaction that needs to be balanced. Then we write an equation for each element. We list out the variables A, B, C, D, however many substances we had. Then step 5, this is the big one. We have what's called a let. We let any variable equal any number you want. I typically use A equals 2, just because A tends to only be in 1, maybe 2 compounds, and 2 because it's easy to work with, easy to multiply, easy to divide with. After we've got our let, we solve each equation, and if it turns out that we end up with a fraction, we simply multiply that fraction and any other coefficients or variables that we've already solved for by the denominator of that fraction. Lastly, our answers become the coefficients, and if possible, we reduce coefficients to the lowest whole number values. So let's go on and take a look at a couple of examples of this. So the first one is methane plus oxygen yields CO2 and H2O. This is one that could probably be easily balanced using trial and error, but I'm going to show you algebraically. All right. So first thing I want to do again is label each substance. So A, B, C, and D. Next thing I want to do is list out my elements to be balanced. Well, I have carbon that needs to be balanced. I have hydrogen that needs to be balanced. I have oxygen that needs to be balanced. And once I reach my arrow, I should not have anything on the product side that I haven't already accounted for on the reactant side. So in this reaction, I have carbon, hydrogen, and oxygen to balance. So now we're ready to write our equations. So I'm looking at the subscripts for the substance. So in looking at carbon, I have one carbon within substance A. So its equation tells me I've got one carbon within A. I don't have any in B, so I don't have to include it in carbon's equation. My arrow sign becomes an equal, and then I look at my product and I see that there is one carbon within substance C. So in carbon's equation, one carbon within substance C. And there's no carbons in D, so I don't have to include it in carbon's equation. Now I can look at hydrogen. So looking at my reaction equation, there are 4 hydrogens in substance A. So 4 hydrogens in A, none in B. Arrow becomes the equal. I don't have any hydrogens in C. I have 2 hydrogens in D. So 2 hydrogens in D. My equation for hydrogen is 4A equals 2D. Now I can look at oxygen. I don't have any in A, so I don't have to include it in the equation for oxygen. But I have 2 oxygens in B, so 2B. My arrow again becomes an equal, and I have 2 oxygens in C, so 2C, plus I have 1 oxygen in D, so 1D. So these are my equations for carbon, hydrogen, and oxygen. And now it's time to list the variables, so A, B, C, and D. I've got substances A, B, C, and D. And now my let. And again, I'm going to let A equal 2. Now, that value may or may not be correct. And honestly, it doesn't matter. As long as you have your equations set up properly and you solve them correctly, the answers will resolve down to what they need to be for a balanced equation. So once I have my let, I start substituting it in. So I've got the equation 1A, where A is now defined as 2, equals 1C. So solving for C, I would divide both sides by 1, So C would have a value of 2. And I'm done with carbon's equation. Now I can look at hydrogen. 4 times A, where A is 2, equals 2D. Solving for D, I divide both sides by 2. And D equals 4. Now I'm done with hydrogen's equation. And I can look at oxygen's. So 2 times B, where B is still unknown, would equal 2 times C, where C is defined as 2, plus 1 times D, where D is defined as 4. So that gives me 4 plus 1 times 4 is 4. So 4 plus 4 is 8. So 2B equals 8. And solving for B, I divide both sides by 2. So B would equal 8 halves, or 4. Now that I've solved each equation, I look at my variables. A equals 2, B equals 4, C equals 2, D equals 4. And we look to see if we can reduce. And each one of these, I can reduce by a factor of 2. So my coefficients become 1, 2, 1, 2. And those answers now get put into my reaction equation as coefficients. So my first substance would have a coefficient of that unwritten 1. B would have a coefficient of 2. C again would be an unwritten 1. And in front of water, I would have a 2. And then we verify that these are balanced correctly. So I have 1 times 1 for 1 carbon, 1 times 1 for 1 carbon, 1 times 4 for 4, so that I have 4 hydrogens. 2 times 2 gives me 4 hydrogens. 2 times 2 is 4 oxygens. 1 times 2 is 2 oxygens, plus 2 times 1 is another 2 oxygens, for a total of 4 oxygens, and we're balanced. So let's look at another of these. C6H6 plus O2 yields CO2 and H2O. So again, I'm going to label A, B, C, and D. Then I'm going to list my elements. Again, I have carbon, hydrogen, and oxygen. For carbon, there are 6 carbons in A, none in B. Arrow becomes an equal, and I have 1 carbon in C, none in D. For hydrogen, I have 6 hydrogens within A, none in B. Arrow becomes an equal, none in C, and I've got 2 hydrogens in D. Lastly, oxygen, 2 oxygens in B. Arrow becomes an equal, 2 oxygens in C, plus 1 oxygen in D. And to make the equations a little less scary, I don't write the 1s. Not that 1 should really be scary, but now I list my variables. So I have A, B, C, and D. And to show you that this works with any let and any number, I'm going to go on and start out with, we'll say D equals 5. Why not? So if D equals 5, then I have 6A equals 2 times D, where D is 5. So that means 6A would equal 10. Solving for A would equal 10/6. And like I said, because I've got a fraction, I need to get rid of it. So the denominator is a value of 6. So I'm going to multiply that 10/6 by 6 to get 10. And then I'm also going to multiply the variable that I already know by 6. And 5 times 6 gives you 30. And now I start working with 10 and 30. So I can come over. 6 times A, where A is 10, would equal 1C. So that means C would have to equal 60. Now I know those. 2 times B equals 2 times C, where C is 60, plus D, where D is 30. So 2 times 60 is 120 plus 30. So I have 150. equals 2b. And whenever you do the math of 150 divided by 2, what do you get? You get 75. So b would equal 75. And then we look to see, can I reduce each one of these values down? Yeah, I can divide all of them by 5. So 10 divided by 5 is going to give me 2. 75 divided by 5 is going to give me 15. 60 divided by 5 is going to end up giving me 12. And 30 divided by 5 is going to give you 6. Can I reduce my values of 2, 15, 12, and 6 down? Nope. So the coefficient in front of A would be a 2, in front of B would be 15, C would be 12, and D would be 6. And then we verify. 2 times 6 would give me 12 carbons. 12 times 1 is 12 carbons. 2 times 6 is 12 hydrogens. 6 times 2, 12 hydrogens. 15 times 2 is 30 oxygens. Well, 12 times 2 is 24, plus another 6 times 1 is 6. So 24 plus 6 is 30 oxygens, and we're balanced as 2, 15, 12, and 6. Now, I did this starting with D equals 5, and you can see the math gets a little messy, I guess you could say, but it still works out because my equations were correct and I solved those mathematical problems correctly. So it doesn't matter what you start with, but again, as you could see in the first example, starting with A equals 2 typically is your easier process. Okay? So here are 2 other equations that you can work, and then once you've got those worked, just leave me a comment with what your answer is, and I can tell you if you've worked them correctly or not. And in ending out this video, I want to go all the way through the steps that we had for trial and error and start with one where instead of it giving you the chemical formulas, it gives it to you in a sentence format. So you can see how this has worked and what that step 1 and 2 looks like. So in this, it tells me lead 2 sulfate reacts with sodium chloride. Well, if it's reacting with it, then that means that my lead sulfate has to be a reactant and my sodium chloride has to be a reactant. To produce, well, if it's producing, then it's going to be a product. It tells me it produces lead 2 chloride and sodium sulfate. So these would be my products. Okay. So now that's step 1. Step 2 would be to write this out using appropriate symbols. So lead 2 sulfate would have a formula of PbSO4. Reacts with is a plus sign. Sodium chloride would have a formula of NaCl. To produce, that's my yields arrow. And then lead 2 chloride would have the formula of PbCl2. And another plus symbol, sodium sulfate, which would be Na2SO4. And again, I put these little lines in just so I know what needs to be changed and never to change the subscript. So balancing through this, if you look at it, I start with 1 lead and I end with 1 lead. So that's good so far. I start with 1 sulfate group and I end with 1 sulfate group. So that's good. Now then for my sodium, I begin with 1 sodium, but I end with 2. So I want to put a 2 in front of my sodium chloride, which now gives me 2 times 1 for 2 chlorines, and I've got 2 chlorines. So this is balanced out with unwritten 1, 2, unwritten 1, unwritten 1. And that's a full balanced equation by trial and error. Obviously, you could do this by algebraic method, but trial and error is easy enough with this one that trial or algebraic method would just be a lot of time spent to come up with not a whole lot. So there is an appropriate time to use the trial and error method versus using the algebraic method. And I always suggest doing the algebraic method after you've attempted trial and error. Okay, so hopefully all of this has made sense to you. If you have questions or ideas for a video, please leave them in the comments. I'll be sure to reply back to you. Hopefully you found the video helpful, and as always, thanks for joining me.